Hey everybody! Today we're going to do the AP Statistics Quideo number 4. Awesome! So the basic question is asking, the Gallup poll asked a probability sample of 1,785 adults whether they attended church or synagogue during the past week. Suppose that 40% of the adult population did attend. We would like to know the probability that an SRS of size 1,785 would come within plus or minus 3 percentage points of this true value. So part A is asking, if P hat is the proportion of the sample who did attend the church or synagogue, what is the mean of the sampling distribution of P hat? What is its standard deviation? For part A, we found that the mu is 0.4 and the standard deviation formula is the standard deviation equals the square root of P times 1 minus P divided by the N. And then we plugged all the numbers in and we got 0.4 times 0.6 divided by 1,785 to get 0.0116. Part B is asking, explain why you can use the formula for the standard deviation of P hat in this setting. And this is rule of thumb number 1. Rule of thumb number 1 is the population must be 10 times larger than the sample size. Part C is asking, check that you can use the normal approximation for the distribution of P hat, and this is rule of thumb number 2. So what we did is we did the normal approximation NP minus 1,785 times 0.4, and we got 714, which is greater than or equal to 10. And then we did N times 1 minus P equals 1,785 times 0.6, which equals 1,071, which is greater than or equal to 10. In part D, it's asking, find the probability that P hat takes a value between 0.37 and 0.43. Will an SRS of size 1,785 usually give a result P hat within plus or minus 3 percentage points of the true population proportion? Explain. So what I did is I took the equation right here and I got 0.994. So in conclusion, 99.4% of all the samples should give P hat within plus or minus 3% of the population proportion. Moving on to the advanced question. The advanced question is researchers were interested in comparing two methods for estimating tire wear. The first method used the amount of weight lost by a tire. The second method used the amount of wear in the grooves of the tire. A random sample of 16 tires was obtained. Both methods were used to estimate the total distance traveled by each tire. The table below provides the two estimates in thousands of miles for each tire. So this is the table that they're talking about. So part A asks, construct and interpret a 95% confidence interval for the mean difference mu in the estimates from these two methods and the population of tires. So what I did is I used a one sample t-test, and the confidence interval equation is confidence interval equals x bar plus or minus t star times the standard deviation divided by the square root of n. So I got x bar equals 4.556, t star, which I found in table C, equals 2.131, and I got that from finding the df, which equals n minus 1, which is 15, and the standard deviation over the square root of n is 3.226 divided by the square root of 16. Now plugging all of that into the equation, I ended up getting 1.719, and that is 4.556 plus 1.719, which is 6.275, and 4.556 minus 1.719, which is 2.837. And we are 95% confident that the intervals from 2.837 to 6.275 captures the true mean difference. Part B is asking, does your interval in Part A give convincing evidence of a difference in the two methods of estimating tire wear? Justify your answer. So I said we can say that we are 95% confident that the difference between the two methods will fall between the intervals 2.837 and 6.275. So since the difference wasn't zero and there is a positive range, it gives convincing evidence of a difference in the two methods. The AP question. So golf balls must meet a set of 5 standards in order to be used in professional tournaments. One of these standards is distance traveled. When a ball is hit by a mechanical device, iron byron, with a 10-degree angle of launch, a backspin of 42 revolutions per second, and a ball velocity of 235 feet per second, the distance the ball travels may not exceed 291.2 yards. Manufacturers want to develop balls that will travel as close to the 291.2 yards as possible, without exceeding the distance. A particular manufacturer has determined that the distance traveled for the balls it's produced are normally distributed with a standard deviation of 2.8 yards. This manufacturer has a new process that allows it to set the mean distance the ball will travel. So Part A is asking, if the manufacturer sets the mean distance traveled to be equal to 288 yards, what is the probability that a ball is randomly selected for testing will travel too far? So we need to find the probability that a ball that's randomly selected for testing will travel too far. So what I did is I used D for distance. So the distance can't exceed 291.2 yards. So you have to find the z-score. So I did 291.2, which is the number, minus 288, which is the mean, divided by 2.8, which is the standard deviation. And I got, overall everything, I got 0.1271. Part B is asking, assume the mean distance traveled is 288 yards and that 5 balls are independently tested. What is the probability that at least one of the 5 balls will exceed the maximum distance of 291.2 yards? So, what you have to do in this one is you basically have to calculate the probability of at least one of the 5 balls that you were given will exceed 291.2 yards. So for Part B, what we're going to do is we're going to take 1 minus times 1 minus 0.1271, and we're going to multiply all of that by itself 5 times. And we got the 0.1271 from what we did in Part A. So we continue to, and then we do 1 minus the quantity of 1 minus 0.1271, which was 0.8729, and we're going to multiply that by 5, and this is just showing out all the work to do. So this is the original equation, and we're just going to show out all the work that we're going to do, and we're going to get 0.4932. So 49.32% of the balls, or one of the 5 balls, will exceed the maximum distance of 291.2 yards. Part C is asking if the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum distance of 291.2 yards, what is the largest mean that can be used in the manufacturing process? So what I did in Part C is I found the z-score again, so I got 2.33, and I plugged it into the equation, and I got 284.676. And in order to be 99% certain that a randomly selected ball doesn't exceed the maximum distance of 291 yards, the largest mean should be 284.676.